So this is systems of equations with graphs. How do you solve a system of equations using graphs? And what do graphs really tell you? And how do they help you solve systems of equations? Let's take a look at an example to get started. Kathy's Catering charges $50 setup fee and $4 per person for dessert. Diamond Catering does not charge a setup fee, but it does charge $5 per person for dessert. So our task is to write an equation to represent the total cost for each caterer. And I have to remember how to go to full screen. There we go. And to get my pointer. So the $50 setup fee, we're thinking right now about writing an equation that is in slope-intercept form. So this $50 represents our starting point or our intercept, the y-intercept, and this $4 represents our rate of change or our slope for this particular equation. So what we see overall is that we have two unknowns in this situation. We are trying to find the total cost for each caterer, and the other unknown is how many people are going to come to this event. So the total cost changes based on how many people will be in attendance. So you can see here that Kathy's Catering is going to, let's think of this event. We're in the room. The catering company has set up the table. They have the servers in place. The food is in place. And I pay them $50. That's what the setup fee needs, is that as soon as they've gotten everything set up, I owe them $50. And then my first person comes and I owe them $4. So if all I've done is have them set up and had one person come, together I owe them $54. The next person comes, I owe them another $4. So now I'm up to $58. The third person comes, I owe them another $4. So now I've got $62. Let's look at what happens with Diamond Catering. Diamond Catering is in the room. They have everything set up. The servers are there. The food is there. I don't owe them anything yet. My first person comes, I give them $5. My second person comes, I give them another $5. Now I've paid them $10. The third person comes, I give them another $5. Now I've paid $15. So with 3 people at my event for Kathy's Catering, I have paid $50 plus $4 a person, that's $12. So I paid $62. But in the situation that I've hired Diamond Catering and I have 3 people at the event, I've only paid $15. So that's what we're doing, is we're writing an equation that represents the total cost, my one unknown, based on how many people are coming to the event. That's my second unknown. And then here are the situations. With Kathy's Catering, I have a y-intercept or a starting point of $50, and my slope or my rate of change is $4 per person. With Diamond Catering, I have no y-intercept, no startup cost, but my rate of change, my slope, is $5 per person. So the first thing we do when we write any equation is to define our variables or say what the unknowns are and what variables we're using for those. So in this situation, what I'm looking for is my total cost of food, and I've called that Y. And my other unknown that I have is the number of people, and I've called that X. So this piece right here is very important. It's called defining your variables. Because a lot of times when we get to the end of doing all this work, we have to remember, wait a minute, what did I call Y? What did I call X? So if you define your variables, write it down at the very beginning. When you get to the end, you'll remember what it is that you have. So how do we write these equations? For Kathy's Catering, we said if we're using the slope-intercept form, we've said that our total costs are equal to our starting point of $50, and then we're going to add our slope times the number of people, our rate of change, $4 times the number of people. And if you remember the slope-intercept form, it's y equals mx plus b. I could have written this as 50 plus 4x, but I'm in the habit of always writing it in y equals mx plus b slope plus my intercept. So that's why I've written it this way. For Diamond Catering, I don't have an intercept. I don't have a starting point over here. My b is equal to 0, in other words. But I do have a rate of change of $5 per person. So my total costs are equal to $5 times the number of people who are coming to my event. So this equation is I can vary my Y depending on how many people I think I want to come to my event. So what number I substitute in for X. What would it cost me if I had 5 people come, 10 people come, 25, 500? Any number of people that I want, I can substitute in for X and find out what my total cost will be. So let's see what that looks like on a graph. Here I use my favorite tool, Desmos, to graph the lines. And here is my equation, y equals 4x plus 50. That's Kathy's Catering, and it shows you right here. That's the purple line. Let's look at the purple line. There's my starting point of 50. And then the slope is a little bit hard to see if we want to just take it as 4/1, but I can also, which is what that would be, $4 for every one person. That's like going up. Let me see, this is 70, nope, 60, 70, 80, 90. So this is going up by 10. So if I go up just a little bit here for 4 and then over halfway, that's 4/1. An easier way of seeing it is to multiply both of those by 10, the 4 and the 1. So I'm multiplying both parts of my fraction by 10 to get an equivalent equation. Instead of 4/1, let's use 40/10. That's a little bit easier to see here. So if I go up 10, 20, 30, 40, and over 10, there's my rise over my run. I can keep going up that way. That's much easier to see. And there's my slope on my line. Here's Diamond Catering. I'm going, my slope is 5/1. Again, if I multiply both that top and bottom, the numerator and the denominator by 10, I'll get a fraction of 50/10. Much easier to see that slope going up using that equivalent fraction. And there's my line for Diamond Catering. So in this equation, this system of equations, which is this 2 equations, I'm looking for this critical point right here. And it's so important that Desmos will show you right away, here's this point where these 2 lines intersect. And that means that this point is exactly the same for both equations. So right here, notice this is my x-axis. It's telling me that for 50 people, I will pay $250. if I invite 50 people to my party. So for both companies, for Kathy's and for Diamond Catering, it is telling me that if I invite 50 people, I will pay the exact same amount, $250. So this point of intersection is a really critical point when I'm looking at systems of equations. It is the solution that is true for both equations. So what that means is I take this point, this x and y for this point right here, and substitute it in for both equations, then it will make the equation true. It will make this y be equal to that x as long as I do these things. It will make this y equal to this x as long as I do these things. What am I talking about? Let's take a look. So a system of equations is two or more equations with the same unknowns. In the catering example that we just looked at, the two unknowns are the total cost, which is my y variable, and the number of people, that's my x variable. Solving a system of equations means finding the solution that makes each equation in the system true. In this case, we're talking about the solution to the system of equations is the same number of people served at the same cost. So for these two equations, it was 50 people would be served for the same amount of money for both catering companies. And we can check this by substituting the numbers into the equation. So what I'm saying is this is the equation for Kathy's catering. If I take the x of 50 and substitute it into the equation, and that y that came up at that point of intersection, which is 250, it should make this equation true. So let's substitute in and solve. My y was 250 and my x was 50. So 250 equals 4 times 50 plus 50. With simplify, 4 times 50 is 200. Simplify again, 200 plus 50 is 250. Is it true that 250 equals 250? It is true. That's what we mean by making the equations true, that the solution makes both equations true. So that's Kathy's catering. It works for that equation. Let's see if it works for the Diamond equation. Y equals 5 times x. We substitute in 50 for the x, 250 for the y, and then we simplify. 250 equals 5 times 50. 5 times 50 is 250. 250 does equal 250. So this, we have proven that that intersection point, which was 50, 250, makes both of these equations true. Let's see what else we can see. Solving a system of equations can also show when one variable is lower or higher, by which I mean, look at this line right here, this equation, which is Kathy's. We can see that the y variable is greater every time when the x is the same. So look at this. When x is 20 here, for Diamond, the total cost, when the number of people is 20, the total cost is $100. But when my number of people is 20 for Kathy's, my total cost is $130. Yep, $130. So even though the x's are the same here, 20 and 20, my y for this top equation, this purple equation, which represents Kathy's, is greater. Let's look at when my number of people is 30. When X is 30, for Diamond Catering, my Y is 150. When X is 30 for Kathy's Catering, my Y, or my total cost, is 170. So it can show us, just looking at this graph, we can see that for every number of persons or people that come to my event, the total cost will be greater until we get to 50. And then what happens? Then you can see that now Diamonds is greater because Diamonds is on top. Look at this. When we get to 60 people, our Diamond Catering Company will cost $300, but Kathy's will only cost $290. So actually, as soon as we pass 50, it's a little bit harder to see what exactly the numbers are here. But if we substitute in 51, 52, 53 into our equation, we'll see that our Y is greater for Diamond Catering than it is for Kathy's Catering. So for each number of people from 0 to 50 or to 49, Kathy's has a greater total cost. At 50, they're the same. And then at 51 and above, Diamond is more expensive. Here's another example. Action Repairs charges $75 flat fee and $80 an hour. Busy Bee Repairs charges $40 a flat fee and then $95 an hour. When are their total costs the same? So again, this idea of a flat fee is that's the starting point. So when the action repair person comes to my door, before they walk in, I have to give them a check for $75. And then I'm going to pay them $80 every hour they're working on my appliance. Busy Bee Repairs person comes to my door. Before they walk in, I am going to pay them $40. And then for every hour they're working on my appliance, I'm paying them $95 an hour. So I want to know, when are their total costs the same? Again, when we write equations, we are going to define our variables. So in this case, Y is our total cost, and X is the number of hours that the repair person is working on my appliances. So we're going to write them in Y equals mx plus b slope-intercept form again. So for action, here's my B, my y-intercept, and here's my slope, my rate, $80 an hour. And so this equation will be y equals 80x plus 75. So that's my slope, and there's my y-intercept. Busy B, here's my y equals the total cost, 95 is my slope, and 40 is my flat rate or my y-intercept or the B. So those are the two equations that I'm going to use. What do they look like when we graph them? So 80, here it is at $75 plus at my starting rate, and then the slope, it goes up $80 per hour. Here's the Busy Bee. It starts at $50 and goes up $95 per hour. And here's the point of intersection. So what does that point mean? 1.667 and then 208.33. Well, we know that the first number that we always see in a point is the X. So this represents the number of hours, and the Y is the second number that we see, 208.33. That's the number of dollars. So what that is telling us is that both companies will charge me the same amount after they've been in my house for an hour and 2/3, 0.667. The fraction equivalent to that decimal is 2/3. So when they're there at my house 1 2/3 hours, or an hour and 40 minutes, I will have paid them the same rate, which would be $208.33. So what we can say is that point of intersection is telling me that in 1 2/3 hours, the total cost for both companies will be $208.33. Now, if all I'm concerned about is money, and I don't know whether the quality, or I think the quality of both repair companies is the same, that they will do an equally good job or equally effective job for me, then I would want to know how long do they think this repair is going to take. If I think it's going to take them an hour or less, then I probably want to go with this purple company here, which was Busy Bee, I think. And if I think it's going to take more than 2 hours, I probably want to go with Action Repair. But if it's right around an hour and a half to 2 hours, then it's kind of too close to call. And maybe I would take whoever came first. Okay, so we just answered this question. Will an Action be cheaper? We can see that the green line is the Action Repair Company, and they are cheaper after we get to an hour and 2/3, because here's where the line is lower. We want to double check. We looked on here at 2 hours. We can see that the total cost is less than 20, 40, 60, less than 220, just a little bit less than 220, where at 2 hours, Busy Bee is right at 200. So we can see that Action will be cheaper after that hour and 2/3, and Busy Bee is cheaper before the hour and 2/3. But right at an hour and 2/3, they'll both be the same. So I have another party that I'm planning, and again, it's a dessert party. I can order a coconut cake for $25 and then pay $2 per person for iced tea, or I can order punch for $15 and pay $3 per person for a cookie tray. Write an equation to represent each situation. So again, what are my unknowns? I want to define my variables. I am looking for, I see that I have per person for each one. So number of people is one of my variables. And I haven't asked the question, but whenever we're talking money, usually the other unknown is total cost. And so my question, I haven't asked it yet, but clearly the question that I'm thinking of is, what will my total cost be for these two situations? So the X is the number of people and Y is my total cost. I'm going to write these in slope-intercept form. So I'm going to say for the cake situation, my total cost will equal 2 times the number of people that I invite plus $25 for the cake. And then for my punch and cookie situation, my total cost will be 3 times the number of persons, $3 times the number of people that I invite, plus $15 for the punch. So what does that look like on my graph? The black line represents my cake and tea. There's my $25 for my cake. And then I go up $2 for every person. So it looks like 22. Oh, nope, these are 5. This is going up by 5, so it's a little bit less than half. Up 2 over 1, up 2 over 1, up 2 over 1. There's my slope for my cake and tea. And for my punch and cookies, what did I just say? 5, 10, 15. Yep, there's my 15 intercept, where I'm starting for my punch, and then I would go up 3 over 1, up 3 over 1. There's my slope. What does this point 1045 represent? Remember, my X always comes first when I'm writing my point. So this is X and this is Y. We defined our variables before, but here it is on my graph. Here's my X-axis, the horizontal one, the number of people. So X represents the number of people. And then my Y variable is the total cost. So what that means is if I invite 10 people to my party, the total cost for both situations would be $45. I would be spending $45 to have cake and tea, or $45 to have punch and cookies, if I invite 10 people. What other information does the graph give you? Well, it tells me that if I invite anywhere up to 10 people, that it would be cheaper to have punch and cookies. Here's my red line is down below. So that's showing me that this is less numbers. Let's check it out. For 5 people, I would be spending $30 if I do punch and cookies. If I invite 5 people for cake and tea, I would be spending $35. Let's look at another situation. For 20 people, it would cost me $65 to serve punch and cookies. And for 20 people, it would cost me $75 to serve cake and tea. Now, what else can I see from here? What if I told you that I had $60 to spend? That was my total amount that I could spend. How many people could I invite for cake and tea? Well, if I look at $60 here and go across, if I have, oops, that's punch and cookies. My red line, I get to first. So I could have 15 people for punch and cookies. But if I keep going over here, I see that I could have 15, 16, 17 and a half people. I'm not sure who my half of a person would be, but I could invite, let's round it down and say 17 people. 17 people for $60. So that might help make my decision. But maybe I really, really want coconut cake, and so I'll just limit my list to 15 people. There are a lot of constraints that you can have on your situation, And cost isn't the only one, but it does help us figure out what other constraints we might be thinking about. So there's that. Are there other information? If I wanted to spend $50, here's $50. The same thing happens. I can invite 11 and a half people or 12 and a half people to my party, depending on which choice I pick, cake or cookies. I have one more example for you. So my mother has been sewing masks, face masks to give to people in nursing homes and hospitals, patients, anywhere, volunteer organizations that require people to come in and wear masks. And my sister started sewing masks too. Now my mom can make 12 masks in an hour, and my sister can make 10 masks in 1 hour. But on one day when I was talking to them, my sister started early, and she had made 5 masks before my mother even got started. So let's write a situation to represent that work on that particular day. First thing we have to do is decide what are the variables in this situation. We have a clue right here in our rate. Here's another way if you're trying to figure out what your variables are going to be. If you have your rate set out, that helps you. Masks per hour. So those are the 2 variables that I'm going to be needing in my equation. Those are my 2 unknowns. But which one goes where? Masks per hour. When you're thinking about your ratio, you're going to say if you've got your masks per hour, the hour, whatever comes after that per, is going to be on the x-axis, the horizontal axis, and then the masks or whatever comes first is going to be your y-axis, because you think about it, we always talk about rise over run. So in this 12 masks, our ratio would look like the fraction 12 over 1. So when we think of rise over 1, this is going to be on the y-axis. This will be the x-axis. So our 2 unknowns are y is the total number of masks, and x is a number of hours. Another way you can think about this is that the number of masks we have depends on the number of hours that they're sewing. So some people think of it that way, that this depends on how many of these we have. So that makes this the independent variable, this the dependent variable. Independent variable always goes on the x-axis. Let's write our equations for this. So my mother can make how many total masks if she can make 12 masks per hour? My sister, how many can she make if she can make 10 masks per hour, but she got started early and she's already made 5? So there's our starting point of 5. My mother had a starting point of 0. She has not made any masks yet that day. So she has a starting point of 0. And then here's her rate, or the slope, 12 masks per hour. Here's the rate, or the slope, 10 masks per hour. So y equals mx, y equals mx plus v. Here it is on a graph. My mother's slope line is the blue line. Here she is. There, her starting point was 0, and then she went up 12 masks every hour. There's her rate, And my sister had a starting point of 5, right there, and then she goes up 10 every hour. Every hour she increases by 10. So what information does the graph give us? Remember, this point of intersection is the solution to our system of equations. Here's our system, y equals 12x, that's one equation. Y equals 10x plus 5, that's our second equation. That makes it a system, and we're looking for the point where they intersect. So the question that we would be answering is, how many hours before they both zone the same number of masks? So given the situation where my sister started with 5 masks already done and then made 10 masks an hour, and my mother started with 0 masks already made and then makes 12 masks an hour, at what point have they made the same number of masks? So remember, this is our x, the number of hours. So in our point here, the x is first, x comma y, so our x is first, so 2.5 hours, they will have made 30 masks each. So my mother at 2.5 hours making 12 masks an hour will have made 30 masks, and my sister making 10 masks an hour, having already started with 5, will also have made 30 masks. So, and we were looking at this like a race. When they first start, who's ahead? My sister. She has 5 masks already made. And at the end of 1 hour, she's still ahead because she has 10, 12, 14. She's now made 15, and my mother has made 12. At 2 hours, my sister is still ahead because she has made 22, 24, 25 masks, and my mother has made 24. So she's got 1 mask ahead. By the time they hit 2.5 hours, they're even. And then from then on, my mother goes ahead and keeps going. So if we could say by what time have they both made 40 masks? Here's the total number of masks, 40. And my mother would have been at 3 and 3. This is a half, so like at 3 1/4, and my sister at 3 1/2. They would have both made. Oh no, that's not a quarter. That's more than that. 3 1/3 and 3 1/2. Then they would have both made 40 masks. But we could check on that by substituting in 40 here and solving. How much time would that have been? What would happen if my sister hadn't started early? If she had just started at the same time as my mother and didn't have 5 mask lead? Then the equation would be y equals 12x for my mother and y equals 10x for my sister. So here's my mother's line, and here's my sister's line. Where is the point of intersection? It's right here at 0, 0. That's the only time that they both have made the same number of masks. My mother would have finished her first one before my sister even got 1. There she is. Oops, this is 50. Way down here, she would have finished her first one, and my sister would not have finished one yet. So as soon as my mother made her first mask, she would have been ahead, and she would have kept ahead until they reached the number of how many masks they were going to make. So the only point of intersection in this system of equations is 0, because 12 times 0 is 0, and 10 times 0 is 0. As soon as we add 1 in, 1 times 12 is 12. 1 times 10 is 10. As soon as we add any number in there, a quarter, 1 million, it doesn't matter. We will never have another point of intersection. 0, 0 is the only point of intersection for this system of equations. What if my sister started early, but she'd gotten faster, and now she can sew 12 masks per hour? Here's what that looks like. Here's my mother. She's the red line. She started at 0, 0, and she can sew 12 masks an hour. But here's my sister, the blue line. She starts at 5 masks, and if she can sew 12 masks an hour, she always stays 5 masks ahead. No matter where you look on this line, she stays 5 masks ahead. Why is that true? Because their slope, the rate of change, is the same. The slope of 12 and 12 means they're the same. So no matter how many hours they sew, if their rate of change, their rate of mass creation stays 12, my sister will always be ahead by 5 masks. That tells you that these two lines are parallel. Lines that have the same slope are parallel. They will never intersect, no matter how far we take this out, how many hours they sew. They will never have the same number of masks. So these are parallel lines. There is no point of intersection. There is no number that we can substitute in to make both of these equations true. Even if we try 0, well, 0 times 12 is 0, so 0 equals 0, that would work. But if we take that same intersection point, 0, 0, or that same point, and we substitute it in, 12 times 0 is 0, plus 5, that does not equal 0. So this will never be true for this equation. You cannot have the same solution for these two equations. There is no solution, no point of intersection ever for this situation. What if they started at the same time and sewed at the same rate? What you can't really see, because I copied this picture on Desmos, is that if I clicked on my mother's equation, if I clicked on my mother's equation, this line would turn red. This is the exact same equation. And in this instance, it's really easy to see because it looks exactly the same. But there are other situations where the equations, if for some reason I had multiplied this and said by both sides of this equation by 5 and said 5y equals 60x, it would still come down to this equation, because to solve for y, I would divide both sides by 5 and it would look like this in the end. So there are some situations where it's not easy to see that it is the same situation, the same equation, until you solve it or graph it and you realize that you've got the exact same situation going on. In this case, if they both keep sewing at the same rate, no matter how many hours they work, they will have the same number of masks. Their lines will always be the same. And we call that having an infinite number of solutions, because no matter which point you pick out on here, whether it's after 2 hours or 4 hours or 6 1/3 hours or 10 3/5 hours, it doesn't matter what number you pick. If you substitute in for x on both of these equations, of course, you're going to get the same y. So we call that having an infinite number of solutions. So systems of equations can have 3 results. They can intersect at one point, which is what we did in the first few situations. We were looking for where will the one solution that makes both of these equations true. I'm looking for where are my costs equal, or when have they made the same number of math. And many times we're just looking for that one point. We can also look at break even, like when do my costs equal my expenses? And I want to know how many of these widgets do I have to make before I start making a profit. That's a very interesting point too. That's called the break-even point. So you can intersect at one point, and this one point is the solution to the system. It makes all the equations in the system true. Or they can have no points of intersection, which means the lines are parallel. There are no solutions, which makes all the equations true. And that was a situation when my sister started with 5 maths ahead of my mother, but then they made 12 maths an hour and the lines were parallel. There was no point at which they had made the same number of maths. And that could also be true, say, if you were trying to figure out your savings. When would you have the same number of savings? If you start $100 ahead of your friend and you save at the same rate every week, you will always have more money, because there will never be a time at which your friend can catch up to you, because you started ahead and now you're saving at the same rate. In order to catch up, your friend has to save a little bit more, and then eventually they will catch up to you, and you will have an intersection, and there will be a time at which you have the same amount of savings. The third situation is that they can have all points in common. The equations could be the same line, so that every solution will make all the equations true. And that is like that last situation where my mother and my sister were making the same number of maths every hour, or if you and your friend save the same amount every week, then you will always have the same amount of money saved up. So that was when we have an infinite number of solutions that make the equations true. So graphing can be really useful in visualizing what's happening in a situation and helping you see the situation. So I recommend graphing when my numbers aren't too big. I also recommend graphing using Desmos, which you can get to at www.desmos.com. And it's a free graphing calculator, very easy and intuitive to use, but they do have a lot of help on there. And you can play around with your graphs and see what makes the most sense to you, and how the situations change depending on how your rates change or how your starting points change. And so that makes it also easy to see. I hope this has been helpful.